Hey everyone, and welcome to this explainer on applied thermal engineering. We are diving straight into the mechanics of how energy moves, transforms, and honestly, literally powers our entire modern infrastructure. So let's kick things off with a pretty massive question. What exactly is thermal engineering? And why is it the absolute key to our energy future? At its core, it's the science of energy transfer. It's all about figuring out how we can take raw heat and turn it into the mechanical work that drives our industries, or on the flip side, how we manipulate temperatures to cool our homes. The stakes here, we're literally talking about the survival and sustainability of human infrastructure.
Today's agenda covers 5 core modules. 1. The energy landscape. 2. Laws of thermodynamics. 3. Energy versus exergy. 4. Thermal machines and cycles. And 5. Heat transfer principles. Let's get right into it.
Module 1. The energy landscape. Understanding the global stakes.
We have to start at the macro level here. Now, what's really interesting is the dramatic projected shift in global energy capacity from 2016 to 2040. Coal is projected to shrink drastically, dropping from 30% of global installed capacity all the way down to just 13%. Meanwhile, utility-scale solar and onshore wind, they're expanding massively. And as we phase out those fossil fuels, applied thermal engineering is the exact thing that provides the deep technical know-how to make all these new, sustainable power systems actually run efficiently.
All right, moving on to Module 2, Laws of Thermodynamics, the ultimate rule book.
To build that efficient future we just talked about, we have to play by the universe's rules. Thermodynamics dictates exactly how we can convert fuel into usable work in an engine. We can't just create energy out of nowhere, right? This transformation is strictly governed by some very foundational physical laws. So let's actually test this with a real question, straight out of a 2024 university engineering exam. In which thermodynamic process is there absolutely no heat flow between the system and its surroundings? Think about that for just a second.
Is it isobaric, isochoric, adiabatic, or isothermal? Well, the correct answer is adiabatic. In a perfectly insulated adiabatic process, zero heat enters or leaves the system. It's a foundational concept for understanding rapid state changes, like what happens inside a high-speed gas turbine compressor.
Which brings us to Module 3, Energy versus Exergy, Quantity versus Quality. This is where the application gets really fascinating, because as it turns out, not all energy is created equal. We have high-grade energy, like electricity, versus low-grade energy, like the heat you get from combustion. So, the crucial point is that high-grade energy is 100% convertible to mechanical work. But low-grade energy, the second law of thermodynamics heavily restricts exactly how much of that heat can actually be transformed into useful work.
And this brings us to a really elegant concept called exergy, or availability. Simply put, it's the maximum theoretical work we can extract from a system as it finally reaches thermodynamic equilibrium with its environment. It's not just about how much energy is sitting there. It's about measuring the true quality of it. Basically, how much can we actually harness before it becomes entirely useless to us?
When you compare theoretical input to reality, the numbers can be a little shocking. Say we input 100 units of energy. Because of thermodynamic imperfections, we might only get 25 units of useful electricity out. That means a massive 75 units are just lost to the surroundings. Exergy analysis is the exact tool engineers use to pinpoint precisely where those losses occur inside a thermal plant, all so we can minimize them.
All right, Module 4, Thermal Machines and Cycles, Engineering at Work. Let's shift gears and look at how engineers physically manipulate these laws in the real world. Take the heat pump, for example. It's absolutely fascinating because its entire job is forcing heat to move against nature. It pulls heat from a cold area and pushes it into a hot area, which, as you might guess, requires net mechanical work to be put into the system to make it happen.
And this brilliantly illustrates how the whole thing flows. Mechanical work, usually labeled W, is inputted directly into the center of the system. That work actively pulls heat out of low-temperature surroundings and pushes it into a higher-temperature body. When you think about it, it's essentially just a refrigerator operating in reverse.
Because we're just moving heat around rather than generating it from scratch, we measure performance using what's called the coefficient of performance, or COP. This is simply the desired effect divided by the net work done. This simple math is exactly why a highly efficient heat pump can actually move far more heat energy than the electrical energy it consumes. It's a real game changer, for sure.
Now, to build these things, engineers model the machines using some pretty complex thermodynamic diagrams, like the pseudo-Stirling cycle. The ultimate goal here is maximizing the exergy efficiency of these cycles. In fact, in high-level applied models, pushing an exergy efficiency to 58.5% is considered a massive, massive success.
Let's move to our final module, Module 5, Heat Transfer Principles, Energy in Motion. Let's see how this all builds together when we look at how thermal energy physically travels through real-world materials. Applied engineering heavily relies on three main mechanisms. First up, thermal diffusivity, which is the controlling property for time-dependent transient conduction. Next is emissivity, which dictates how fast an object emits radiation. And finally, conduction, which is the real heavy lifter for transferring heat directly through solid boundaries.
To put that into perspective, let's ground this in a highly relatable architectural example from our exam materials, comparing steady-state heat conduction in a solid masonry wall versus a composite wall. Engineers actually use thermal conductivity equations to calculate the exact material thickness they need. For instance, if a masonry wall has a heat conduction rate of 80% compared to a composite one, thermodynamics dictates exactly how thick the engineer must build it to maintain thermal equilibrium.
And that brings us full circle. So, armed with the laws of thermodynamics, the solid understanding of exergy, and the mechanics of heat transfer, how will you innovate to solve the global energy crisis? The academic theories we've explored in this explainer today are the exact same tools engineers are using right now out in the field. They're using them to redesign our power grids, build highly efficient thermal machines, and transition us away from fossil fuels. The rulebook of the universe is already written. How we apply it? Well, that is entirely up to you.